At low engine speeds, the volume of air passing into the engine is so small that the depression in the choke tube is insufficient to draw fuel through the main jet. Above the throttle valve, however, there exists a considerable depression, and in some carburetors this is used to effect a second source of fuel supply for slow running conditions. A slow running fuel passage with its own jet leads from the float chamber to an outlet at the lip of the throttle valve, as is shown here. The strong depression at this point gives the necessary pressure difference to create a fuel flow. The size of the slow-running jet is such that it will provide the rich mixture which is required for slow-running conditions. An air bleed opening into the area below the throttle valve assists atomization. The purpose of the transverse passage drilled through the throttle valve is to evenly distribute the mixture over the area of the induction manifold. A small hole in the transverse passage, which communicates with the high-pressure side of the throttle valve, acts as an air bleed. It draws fuel through the transverse passage to mix with the air passing to the engine. As the throttle is opened, the depression at the lip of the throttle valve decreases, and the depression in the venturi increases, to the point where the main jet starts to deliver fuel, and the flow through the slow-running system diminishes. Carburetors must be carefully tuned in order to obtain a smooth, progressive changeover between the slow-running and the main system to prevent flat spots. A flat spot is a period of poor response to throttle opening caused by a temporary weak mixture. It normally makes itself felt as a hesitation during engine acceleration. An idle cut-off valve is usually incorporated in the slow-running passage and is used when stopping the engine. When the cut-off is operated, the valve moves over to block the passage to the slow-running delivery. The mixture being delivered to the engine becomes progressively weaker until it will not support combustion and the engine stops. This prevents any possibility of the engine continuing to run erratically due to pre-ignition, and also prevents fuel condensing in the cylinders, which would tend to wash the oil from the cylinder walls, causing lack of lubrication when the engine is next started. The idle cutoff may be a separate control, or it may be incorporated in the mixture control lever, as is the case with the Seneca system illustrated here. As altitude increases, the weight of air drawn into the cylinder decreases, because the air density decreases. For a given intake velocity, the pressure drop in the venturi will decrease as ambient density decreases. However, the amount of fuel which is flowing due to that pressure drop will not decrease by the same proportion, and so the mixture will become richer. This progressive richness with increased altitude is unacceptable for economic operation. With a needle-type mixture control, such as that illustrated here, a cockpit lever is connected to a needle valve in the float chamber. Movement of the cockpit lever inserts or extracts the needle and varies fuel flow through an orifice to the main jet. The position of the needle, therefore, controls the mixture strength. And in the fully inserted position, it will block fuel flow to the main jet, thus providing a means of stopping the engine. The smallest orifice in the whole fuel system is the fuel jet. To prevent any blockage of the jets by dirt or debris, a fuel strainer can be fitted just before them in the fuel line. The air bleed mixture control shown here operates by controlling the air pressure in the float chamber, thus varying the pressure differential acting on the fuel. A small air bleed between the float chamber and the venturi tends to reduce air pressure in the float chamber, and a valve connected to a cockpit lever controls the flow of air into the float chamber. When this valve is fully open, the air pressure within the float chamber is greatest, as is the differential pressure between the venturi and the float chamber, and the mixture is fully rich. As the valve is progressively closed, the air pressure in the float chamber decreases, as does the differential between the chamber and the venturi. Thus, the flow of fuel through the main jet reduces, weakening the mixture. In the carburetor illustrated, the valve also includes a pipe connection to the engine side of the throttle valve. When this pipe is connected to the float chamber by moving the cockpit control to the idle cut-off position, float chamber air pressure is reduced and fuel ceases to flow, thus stopping the engine. At power settings above the cruising range, a richer mixture is required to prevent detonation. This rich mixture may be provided by an additional fuel supply, or by setting the carburetor to provide a rich mixture for high power and then bleeding off float chamber pressure to reduce fuel flow for cruising. This diagram illustrates a type of carburetor with an additional needle valve, which may be known as a power jet or an enrichment jet. The needle valve, which is connected to the throttle control, is fully closed at all throttle settings below that required to give maximum cruising power at sea level. As the throttle is opened above this setting, the needle valve opens progressively until, at full throttle, it's fully open. On some engines, the power jet is operated independently of the throttle by means of a sealed bellows which is actuated by manifold pressure. In this way, high power enrichment is related to engine power rather than to throttle position. A back suction economizer, as illustrated in this diagram, is used to automatically weaken the mixture for economical cruising. When the throttle valve is set at a high power setting, the pressure of air flowing past the valve is only slightly below atmospheric pressure and will have little effect on air pressure in the float chamber. Thus, a rich mixture will be provided. As the throttle is closed to the cruising position, air flowing past the throttle valve creates a suction, which is applied to the float chamber through the economizer channel and the air jet. The reduced float chamber pressure reduces fuel flow through the main jet to provide the economical mixture required for cruising. If the throttle valve is opened quickly, airflow responds almost immediately, and a larger volume of air flows through the carburetor. The fuel metering system, however, responds less quickly to the changing conditions, and a temporary weakening of the mixture will occur, known as a flat spot, or at worst it will cause a weak cut before fuel flow again matches airflow. This condition is overcome by fitting an accelerator pump, which is linked directly to the throttle, and forces fuel into the venturi whenever the throttle is opened. This type of accelerator pump is illustrated here. In some accelerator pumps, a controlled bleed past the pump piston allows the throttle to be opened slowly without passing fuel to the engine. In other accelerator pumps, an additional delayed action plunger is incorporated to supply an extra quantity of fuel to the engine for a few seconds after throttle movement has ceased. Normally, a priming pump would supply fuel to the induction manifold close to the inlet valve. In the absence of such a device, it is permissible on some aircraft to prime the engine by pumping the throttle, exercising the accelerator pump, several times. The practice of pumping the throttle must be discouraged in any other circumstance, because it increases the chance of carburetor fires. A simple light aircraft fuel system is shown here. The fuel tanks are rigid tanks fitted in the wings and filled by the over-wing method. The fuel is drawn from the tanks by mechanical or electrical fuel pumps, through a tank selector and filter or fuel strainer, before being delivered to the carburetor. Engine priming is achieved by use of a priming pump, which takes fuel from the filter housing and delivers it to the inlet manifold. The fuel system is monitored for contents and pressure, and the fuel drains allow any water to be removed before flight.